This week's experiment is related to the acceleration of an object on an inclined plane. The important or overarching focus of this experiment is that we're going to be dealing with an accelerated object as opposed to an object that's moving with constant speed. This will be an object whose speed is increasing at a regular rate with respect to time. The ultimate objective here is to determine the acceleration of the cart on an incline of constant slope. Again, we want to determine the acceleration of the cart. We want to know the rate at which its speed is changing with respect to time. So what we're going to do here is we're going to have an air track, which is this aluminum block, and we're going to have an air cart on the track. This will already be inclined, and we'll use some masses or a spacer at the bottom to incline it at one end. And it's important that you don't remove this. We want to keep this at a constant incline because it's this incline that will determine the rate at which the cart accelerates. So don't move or don't knock this off. If you do, just make sure that you reset it, and you may have to recollect your data. What you want to do is, because you're going to be determining the rate of the change in velocity of the cart, you want to determine the value of the velocity or speed at individual points along the track. So we're going to be using 5 points along the track that we're going to use for positions that we'll make measurements of. Because you want a nice, even starting point, you'll want to use this starting block here, which is adjustable. You'll want to use the starting block so that your cart can be returned to the same position each time. So if I, for example, want the cart to start at the 20 centimeter marker, I'm going to position my starting block so that the leading edge of the air cart glider is at the 20 centimeter position. And then we're going to lock that in. Once it's locked in, every time I return the cart to that position, I'll be at that 20 centimeter marker. It's important that for all calculations that you make for distance, they need to be made relative to that marker. So for example, if you decide that your first distance measure is going to be maybe 50 centimeters away, then you'll want to set it so that you come down here to the 70 centimeter marker position. The distance between these 2 points will be 50 centimeters, and that'll be a half of a meter. And this is really all you end up caring about is the distance between these 2 points. This is delta x, the distance that the cart will travel in that first trial. I should say delta x of the track, because we're going to discuss another distance later on that's much smaller. So as the cart travels on the track, it gets faster and faster and faster. And we're going to discuss one of the first things we're going to use to determine the speed of the cart. We want to know how fast it's moving at, say, the 70 centimeter marker position, because that'll give me 50 centimeters in between the 2 points. To do this, I'm going to use what's called a laser photo gate. So this is the first time we'll be using this. And the laser photo gate is connected to a digital interface, which will be connected to a laptop, where it will determine the time that it takes for this laser beam to be broken. And you can see that at the top of the photo gate, there's a small LED that will indicate whenever that beam is broken. As long as that LED is on, that is the time of passing through that laser. So I can do it either very quickly or I can do it very slowly. And the longer that LED is on, the longer the time is being recognized by that collector. So what we're going to do here is, the first thing is, we're going to use to determine the speed of the cart at the 70 centimeter position is going to be the time that it takes this flag width to pass through the laser beam. Now, because we started at the 20 centimeter position at the leading edge, we want this position to be measured when the leading edge is at the 70 centimeter marker. You don't need to use these values for your displacement. This is just an example. It's a convenient example, but in order to make sure that the photo gate is positioned correctly, I don't want to have my photo gate at the 70 centimeter position because the flag's not at that point. So what I will do is, once I set my air cart to the desired position, I'll use the photo gate to slide it back. And you can't see this from your point of view, but I'm watching the LED on the top, and I'll know that I'm at the correct position as I slowly move this, because the LED will turn on and there it goes. I've gone too far. I can barely see on the camera the LED is on. So what I'm going to do is I'm going to back it off just a little bit until it turns off. Now the moment that this flag moves just even further closer, it's going to cause the LED to turn back on, and that's going to start the reading for the time at that position. You'll use, to measure the speed of the cart, what is called a calculation for distance divided by time. What's the distance? Well, the distance is going to be this flag width. And so from last week, we used the calipers to make the measurement for diameter. But here we're going to take the flag and we're going to put it in the middle of the outside jaws to get a measurement. And with that measurement, we'll have delta x of the flag. This will be the distance that will not change the entire time of the experiment, because this is a constant distance, the width of the flag. It's important that when you do set your flag width, that flag is parallel with the spine of the air cart. So you're going to try as best as you can to line it up parallel so that you're not getting a distance that's something like only the distance between here. You want to get the distance between the 2 points on the flag, the edges of the flag. So we're going to make sure that's parallel, so that as the cart passes through, it will give you that full flag width. So here's my distance. The laser photo gate will give me my time as viewed from the laptop, and the distance of the flag width divided by the time measured on the laptop will give me my instantaneous speed at this position. Now, instantaneous here is in quotes because you can keep getting smaller and smaller with the flag width and smaller values of time. You'll never truly get an instantaneous speed, but it's instantaneous for our purposes. We'll do this at 5 different positions, and so we'll have 5 different instantaneous values for the speed. It should make sense that if this object is accelerating, it's going to have a velocity value here, or speed value here, and at a position down the road, it's going to be a higher speed value because you're moving faster. And so we will be able to use those values for speed at individual locations to ultimately calculate the value for the acceleration or the rate of velocity or speed change. Now, simultaneously, you're going to be using another method to determine the cart speed at a particular speed, and that's using the stopwatch. It's important you realize that what we're really going to be doing here is running 2 experiments. The photo gate is going to give a measurement for the instantaneous time at this position, whereas the stopwatch is going to be used to measure the aggregate time from the starting position to where it passes. Now, it may not be immediately evident how it is that you're going to get an instantaneous time using a stopwatch or instantaneous speed, but because these carts are released from rest, with the stopwatch, person at the position of interest, in this case the 70 centimeter marker, that person is going to use their stopwatch and they're going to get eye level with this marker, and they're going to have a method of synchronization with the person who's releasing the cart. Say 3, 2, 1, go. And the entire time the cart is going down, the stopwatch is collecting time. And the moment that the leading edge of that cart reaches your area of interest, you'll stop the stopwatch. So, because we have 2 simultaneous experiments going on here, it might not make sense immediately, but we need to realize that the photo laser gate is going to be measuring time only for the flag width passing through the laser. It's going to be a small value. The stopwatch person is going to be collecting a time for the entirety of the trip. And this isn't immediately clear as to why you'll do this, but you're going to use that time to find the average speed of the cart to that point. And you might be thinking, why do I care about the average speed? It's the instantaneous speed that I care about. Well, we're going to use the average speed to determine the instantaneous speed, knowing that the cart started from rest. And that's something that you will be able to find in the handout for this week's experiment. So, to wrap this up, ultimately you're going to be using this experiment to determine the acceleration of the glider. We're essentially going to be using 2 different methods to determine that acceleration. This is the raw data collection portion, and you're going to use those data and Microsoft Excel to be able to generate plots for the motion of the cart. You'll generate 4 different motion plots, and you're going to relate them to 3 different motion equations as laid out in the handout for this week's experiment.